Yeah, thank you for coming. I assume some of you are like going back-to-back talks today, so I'll try and keep this lively and hopefully at the end leave plenty of time if people have questions. I'll just say in advance also, I know it's the end of the day, so if you don't have questions, that's okay, but I'm happy to follow up either later or one-on-one. So what I'd like to talk about today is scarcity. And there are lots of different kinds of scarcity. There's scarcity of food, scarcity of energy, scarcity of water. And one of the interesting things about scarcity is that when things are scarce, it almost always leads to some kind of adaptation. So plants, for example, that lie dormant until water comes or spread their seeds widely in the desert, waiting for enough rain to gather for the seeds to successfully germinate. I don't want to talk about a particular kind of scarcity today. It's scarcity of data. Now, data has been scarce since essentially we've had science. It was scarce when Tycho Brahe spent his entire lifetime in Copenhagen carefully recording the positions of planets and stars in the sky, which then Tycho Brahe was able to use to construct his laws of planetary motion, which Newton was then able to use in order to construct his theory of gravity. Data was scarce when Ronald Fisher was developing some of the mathematics that we still use today in inference testing. It was scarce when Clifford Geertz was writing in the 1950s about thick description and cockfights in Bali. It was scarce when Barbara Entwistle was developing some of the mathematics that we now know today as hierarchical linear modeling. And it was scarce when Emma Tarlow wrote her award-winning Entanglement, The Secret Lives of Hair. The interesting thing about scarcity is that these two broad research traditions, qualitative and quantitative, respond to scarcity differently. So, in a qualitative study, typically researchers pick a small number of instances or cases or people, but collect a lot of data about those examples. In contrast, on the qualitative side, qualitative researchers look to have very large sample sizes, collect lots of data about lots of instances or examples, but collect only a very little bit of data about each one. In other words, both quantitative and qualitative data are responses to scarcity. And here's the thing, let me say that again. Both quantitative and qualitative approaches to analyzing data are responses to scarcity. Now, why is that such a big issue? Well, data is not scarce anymore. In fact, the bigger problem that we have is how to take the masses of data that are generated every day in schools and everywhere else and turn them into some kind of pattern that actually winds up being meaningful and not just one of the many patterns that drifts around if you have enough data. I'm going to argue that in order to do that, qualitative methods are not sufficient and quantitative methods alone are not sufficient. We have to find some way of combining them, hopefully more effectively than that. Now, you might think, well, why is big data why is having lots of data a problem for qualitative researchers? I mean, after all, qualitative researchers are only looking at a small number of subjects. What does it matter if there are a lot of other subjects and a lot of other data that could be available? Well, for one thing, it's making the study way underpowered, right? You're leaving tons of data unexamined. But worse, it's possible to fall victim to confirmation bias. When you have lots and lots of examples to choose from, you can cherry pick the examples that fit your preconceived notions. Similarly, you might think, well, quantitative data, I mean, the whole point is to have lots of data, right? That's what we're trying to do. We collect only a little bit of data so we can get a lot of it. Well, right, in general, the idea of quantitative analysis is we take some sample of data. Let's pretend, for example, the people in this room. And we take some measurement. Let's pretend, for example, I measured everybody's height. Right? So let's say the average height is 5'6". And then the idea is to use that sample to generalize about some larger population. For example, since the average height in this room is 5'6", the average height of everyone in the state of California is probably 5'6", right? Well, no, clearly that would be pretty silly. It's what we would call a false positive or type 1 error. Right? It's generalizing from too small a sample or a sample with properties that aren't robust enough to make a claim about a larger population. We measure this with everybody's favorite p-value, right? P-value is greater than some alpha threshold. We conclude that the results are no good. So having lots of data would be good, right? Because if I have more data, I get a bigger sample. A bigger sample means that I can get a lower p-value, right? And I'll find something that's statistically significant. So here's the thing about statistical significance. It follows roughly this equation. what this means is that as the n gets large, as the number of data points gets large, p gets small, and that's generally good, right? You have more statistical power. But as n gets really, really, really large, p gets really, really, really small. In other words, the purpose of statistics is to determine whether or not we have enough data to make a particular claim. But what happens in a world where we always have enough data to make a particular claim? Now, one approach is to think about looking at some version of effect sizes. One way to measure that is with an R-squared statistic, right? An R-squared statistic, I assume actually everybody in this room already knows, but an R-squared of 0.9 or 90% means that 90% of one thing can be explained by another. So for example, height and weight show a correlation of about 50%, R-squared 50%, which means that half the differences in people's weight can be accounted for by differences in their height. Wealth and happiness are also related, so a quarter of people's happiness can be accounted for by their wealth. We should be quick to point out, though, that it's also possible that a quarter of people's wealth can be accounted for by their happiness, which I find actually a more uplifting way of looking at it. All of which is just to say that we can use correlations, the relationship between two things, to measure the size of impact. So for example, meta-analyses done over many, many, many studies, so there's all sorts of flaws in the process of drawing conclusions from that, but that roughly speaking, teacher feedback across many studies has about a 24% impact on student learning, right? So if you get good teacher feedback, your scores are likely to go up by 24% or so. Peer tutoring, 6%, and even if those exact numbers aren't precise or aren't correct because we've aggregated across many studies, the point is that peer tutoring has a positive influence and probably not as big an influence as teacher feedback, and that probably doesn't surprise anybody. Similarly, we could talk about simulation games, instructional media. For those of you who are keeping score, one grade level is actually normed on standardized tests to account for about a 6% difference, which I find kind of distressing given that you spend a whole year in school and all you're expected to go up by is 6%, but there you have it. It corresponds to an effect size of about 0.5. Anyway, this is important because this formula isn't exactly the formula. The formula is much closer to this. So as n goes up, it's true that p goes down. But as n goes way, way up, r squared gets very, very small. Let me give you some examples of why that's a problem. So example number one. You all probably have a smartphone in your pocket, right? And as a result, Amazon and Google and a whole bunch of other internet providers probably know where you've walked. They may even know where you eat, how well you slept. Just to give a quick example, we have a garden at our home, and the hose broke, and my wife asked me to go buy a new one, so I went on Amazon and ordered a hose. And for the next 2 months, all Amazon was showing me was ads for hoses, right? And gardening books, and gardening videos. And so it has all this data about me. I mean, we shop for tons of stuff on Amazon. They have an incredible user profile, and the best they were able to do is say, well, you bought something for your garden, so let's just keep offering you more things for your garden. I actually did a little test, so I have a book that came out not long ago, and you can pay for ads on Amazon. It's incredibly cheap, it turns out. So for a few weeks, I paid for ads just to see, how well it would work. And as you can see, in 1 week, 225,000 people saw an ad for my book, which is kind of mind-boggling if you think about it. But how many of the people actually clicked on that ad? Yeah, well, not so many. And of the people who clicked on the ad, how many of them actually went and bought the book? Yeah, that's an even smaller number still. So if you think about it, those impressions were right about 0.0002% of the time. Right? Now, just think about that. If we were in the business of providing, let's say, automated feedback that we suggested teachers could use in their classrooms, and if the teachers felt that that feedback was useful 0.0002% of the time, we would very quickly be out of business and we would conclude that our feedback system wasn't worth anything. The point being that if that's as good as Amazon can do, what does that mean when you're dealing with an even harder set of problems? Here's example 2. This is from a study of Dragonbox. It's an educational game. For those of you who aren't familiar, you learn algebra by dragging numbers and symbols and dragon heads and other things across a number line or across an equation. So in this case, you take -4 from both sides, you combine, and the equation simplifies. So in this study, researchers were looking at data from 24,000 students. Those of you who do research in schools, I'd just like to ask you, imagine having suddenly data for 24,000 students. They had 21 million data points, because of course the students were doing lots of things while they were playing the game. And they were looking at 540,000 moves and combinations of moves as the variables of interest. So things like adding A on both sides, subtracting A on both sides, subtracting A on both sides with merging, and so on. There's 540,000 of them. And they use what I think in the world of education we would think of as a very conservative p-value, 0.001. Now, let's just point out that with a p-value of 0.001 and 540,000 moves, that 540 of them were likely to be significant just by chance alone. But worse than that, if you do the mathematics behind do the power analysis, basically, what you'll find is that that any one move was going to explain 0.00025% of the differences observed in performance of students playing the game, which amounts to 1.4 seconds of instruction. Now, I know that all of us would like to be 1.4 seconds more efficient in our instruction, but the question is, how important is any one of those pieces of information that we've just found? Example 3. This is from a group of scholars who were examining the PISA data, international data about student performance, and they were particularly interested in data from Finland, because Finland is one of the few countries where girls perform better in mathematics than boys. So they were using data mining of the PISA data to try and figure out what was going on. This is just part of their conclusion. So they concluded those students who are socially and economically less advantaged, have high anxiety towards mathematics, and low self-concept in mathematics, but still clearly above average attitude towards school, are girls who perform below level 3. Now, I've read this many times, because I've given this talk many times, and I still have absolutely no idea what that really means. And I'm 100% convinced that even if you told me what it meant, I wouldn't know what to do with it in an educational context. Fourth example. So one of the things that has been studied a lot in cognitive science is chess. I suspect that's because cognitive scientists like to play chess. But if you were to look across many, many studies of chess, one of the most consistent things that you would find is that in general, experts move their pieces faster than novices, right? Experts move pieces faster. And the single worst piece of advice you could give to a novice learning to play chess is, well, just move your pieces faster. In other words, when we think about data mining, we think about a science with tools that are well understood, and we map the landscape and we come back with these insights that are buried deep underground. When in fact, a lot of what happens, and perhaps too much, is much more like data prospecting, where we take some tools and we sift through data and we hope that we can find some nuggets that we might be able to use somewhere. If we're going to go past that, if we're going to find some combination of qualitative and quantitative methods, whatever that combination is, we're going to have to be able to identify things that are actually important. We're going to need to be able to know what those things mean, and we're going to be able to know that we're not just looking at isolated examples. And to address this challenge, I suggest that we start with ethnography. Why ethnography? Well, as we live in a world where increasingly things that people learn and things that people do involve complex and collaborative situations, where you're not just learning basic facts and basic skills, learning is actually a process of enculturation. Let me give you a quick example of this. It's drawn from the work of Charles Goodwin. What it means for learning to be a process of enculturation is that you have to acquire what Jim G calls a big D discourse, right? A socially accepted association among ways of using language, of thinking, of feeling, believing, valuing, and acting. The way you are in the world that is part of some group in the world that does some sort of socially valuable work. So here's the example. I grew up in New York City, and so when I see a patch of dirt on the ground, pretty much there's only one thing I'm thinking, which is it so wet that I'm going to get my shoes dirty if I step in it? If I were an archaeologist, on the other hand, I would be looking for something totally different. I'd be looking at a piece of dirt as a possible source of evidence of things that happened in the past. Things like post holes, right? So somebody in the long distant past dug out a hole and put usually wood into it. And when over thousands and thousands of years, as the material rots away and gets covered, it leaves a slightly different color of material where the post hole was. Which explains why archaeologists spend so much time working with Munsell color charts, which are tools that they use to collect and carefully grade the color of soil in different places. In other words, things like soil and Munsell color charts and post holes, these are what Goodwin calls codes. And now I'm using big C code because it's part of the big C discourse. These are things that are important in some discourse, in some culture in the world. And a code is just a culturally relevant and meaningful part of a discourse. And if you don't believe that post holes are a culturally relevant and meaningful part of archaeology, I ask you to consider that one of their journals is called The Post Hole. But notice also that it's not just that archaeologists understand what a Munsell color chart is, and they think about soil and they care about post holes. They actually use a Munsell color chart in order to analyze soil, to be able to get information about post holes. In other words, these things are connected to one another. So if learning is a process of enculturation, where we understand a culture by understanding the things that people think and do and care and believe, we understand that by looking for codes, the things that are important and meaningful within that discourse, and how those codes are systematically related to one another. So let me give you another concrete example, this time from some actual data. So this is from an educational simulation that we built and tested over a number of years in my lab. In the simulation, students are building a robotic exoskeleton, so a skeleton that helps rescue workers travel long distances, lift heavier weights, those kinds of things. The simulation had students working in teams, where each team focused on one part of the robotic exoskeleton design. And then the teams regrouped, and now each of the new teams had information about all the different parts of the design across the different folks in the team. And what I'm going to show you is just data from one of those groups right after they've recombined. So these students are communicating over chat, which is why we have a nice record of their data. But their conversation starts when Justin, who's their mentor, asks them to introduce themselves and talk about what part of the problem they have experience with. Basically, he's making an explicit call for collaboration. And then we see that the students follow by introducing themselves and talking about what their past experience was. And the conversation takes a turn when Daniel says, so what was everyone's result? Okay, so what did you actually get, is essentially what he's asking. And now we see the students talk about devices that they had developed in terms of the technical requirements. So for example, Zachary says, we built a device where the safety was close to the company requirement. Daniel says we were able to reach all the internal consultants' requests, and so on. And the conversation takes another turn when Michael then says, yeah, but what were the actual results? He's making a call for people to tell him about the data that they got. And now we see the students start to talk about data. So for example, Zachary is talking about what the payload is, Rena is talking about the safety measures and the costs, Gabrielle's talking about the recharge interval, that's what ROC is. So now they're kind of laying their data on the table, and this ultimately leads Elizabeth to say, well, we need to determine which attributes are the most important so we can meet those requirements and so on. And she makes a call for actually entering a process, part of the design process, where they start trading off because they can't actually maximize every dimension of the problem. Okay, and C. So I've just told you a story about 4 different codes in the discourse of engineering, or at least the discourse of engineering in this simulation. Collaboration, technical requirements, data and design trade-offs. And the connection is that the collaborative discussion essentially launches into a discussion of the technical requirements of the devices, which then gets converted into a conversation about data, and finally the data leads to making this connection about design trade-offs. Now notice when I told you this little story, I had to do one very important thing. I had to actually point at places in the data where I had evidence that people were concerned about things like technical requirements and data. Now, there's nothing magical here. People who do ethnography and other forms of qualitative research do this all the time. It's called a code book. Right? You identify the particular codes that you care about in the data that you're looking at. You write a definition, you provide examples. In other words, if we're trying to do this and we're trying to identify the culturally relevant and meaningful aspects of discourse, that is the codes, right? We have to go somehow from discourse, small d discourse now, the things that actually happened, that people actually said and did. We have to be able to go from discourse to codes. Well, actually, it's even trickier than that, because we don't actually have the discourse. What we have is some record of the discourse, a field note or a log file or something. And we have to be able to go from one to the other. And the concept that gets us there is the idea of a small c code. Right? So if the big C code are the culturally relevant and meaningful aspects of a discourse, then the small c codes are the things that count as evidence or warrants for the big C codes in the discourse. And this notion of a small c code lets us build this bridge. And this bridge, from the small c codes to the big C codes, is the critical part of this kind of data analysis. Why? Because that's what takes us from the world of data on the left to the world of interpretation on the right. It's what lets us think about how the individual codes and how those codes are related in the discourse by looking at the individual codes and how the small c codes are related in the data itself. Not surprisingly then, validation is an important question, right? If your argument at some level rests on this bridge between data and interpretation, you want to make sure that you have some evidence that that's accurate. So typically the way we do this is by picking some code, let's say data, and we ask one rater to rate the data. It's usually a graduate student. And the graduate student goes line by line and says, they're not talking about data here, they are talking about data here, they are talking about data here, and so on. Then we recruit a second person, usually a friend of the graduate student who's doing the dissertation. And we hide the first rater's ratings, and then the second rater goes through similarly and rates the data. And now we compare the two. Not surprisingly, sometimes they'll agree, and sometimes they'll disagree. This is often done with two humans, but increasingly we do it with a human and a computer. And that has the advantage of being able to create an automated classifier, right? Because once you've got agreement between a human and a machine, and actually technically you want agreement between two humans and then between each of those humans and whatever the machine processes. But once you have that level of agreement, now you can code data automatically with some confidence. There are a number of different measures that people use. Kappa is pretty common in educational sciences. And what you're looking for is that kappa, or whatever your measure is, F statistic or Jackards J or whatever, is above some threshold. Kappa of 0.65 is fairly typical again in our field. And here's the thing. This process that I just described, that basically everyone does, is fundamentally broken. I don't mean broken in the sense that some people take their data and throw it into like a topic model or some other unsupervised learning and get back lists of bags of words and then try and interpret those as a matter of coding. Because of course, the bags of words that the machines produce aren't necessarily the codes that you were originally interested in. Nor even like in the trivial sense that people sometimes say, well, our overall agreement across a number of codes was good, as if the fact that we agree generally means that we're going to agree on politics or on what kind of food we should eat for dinner. No, even when everybody does it just the way you're supposed to, it's still broken. And it's broken because it's fundamentally a sampling problem, right? So we agreed that if I take a sample and measure the average, I can't necessarily just generalize to the whole population, right? At least not without controlling for my type 1 error rate or my false positives. Well, same thing is happening here. The two codes that the raters make are actually just a sample from all the data that they could possibly have coded. Right? So we have a sampling problem in the sense that we take this sample, strings of ones and zeros basically, and we measure them. In this case we measure kappa, right? And then we just make an assumption that if that kappa is good, then the kappa will be good across the whole data set. And it turns out that that assumption is wrong if we don't control for type 1 error. Now, how common is this? When I say common, well, we looked at the two most prominent journals in my field, although we've actually looked at a number of other journals too in the education literature. We found over the entire life of the Journal of Learning Sciences and the International Journal of Computer Supported Collaborative Learning that there were 44 articles that used kappa. They computed 141 kappa values, and the number of times they controlled for type 1 error was 0. Now, so you could say, well, is this really a problem? I mean, what's going on, right, is, so imagine that you had a huge, one data set, 10,000 lines of data that were coded by 2 raters. Well, I could measure the actual kappa of that set, and then I could take a test set, similar to however the test set was taken when you were doing your intraday reliability, and I could compute its kappa, right? And the problem would be if the kappa of the test set has acceptable agreement, but the kappa of the whole data set doesn't. This would be the false one or false positive error rate. So we did a Monte Carlo study, which sadly is not as much fun as it sounds. We just created a whole bunch of test sets and a whole bunch of data sets, coding sets, and sampled them, right? And we computed how often false positives occurred under the usual conditions of coding. So test sets from as short as 20, which is shorter than most people use, to 800, which is about the longest that I've ever been able to get a graduate student to code a test set. And frequencies anywhere from 1 in 100 to all the way up to 0.5. Yeah, the false positive error rates are bad. And they're particularly bad right here in the section where most of the work in our field takes place. Codes that are occurring, 10%, 5% of the time, and where our test sets are like, somewhere between 100 and 200. We have type 1 errors that are, the best is down at 1.2, 12%, and it goes up basically up to 30%. And just think about what that means. That means that in any qualitative study that you've ever looked at, if they have 6 codes that they've used, which is pretty typical, there's a 74% chance that at least one of those codes is wrong. In other words, everything that we do is suspect because of this problem. Now, for those of you who say, well, I don't use Cohen's kappa, I use percent positive agreement. Well, you have the same problem. You have the same problem with recall, with precision, with F statistics. Every statistic we've tested has the same problem. And the problem is not with statistic, it's with not controlling for type 1 error, which nobody would do in any other statistical circumstance. The reason it happens here is that the distributions for kappa and basically all these other test statistics are non-normal, which means that even Cohen, who invented kappa, and Cronbach, who invented alpha, right, weren't able to figure out how to analytically derive a confidence interval. Meaning there was no way for them to figure out what the confidence interval should be using a formula. So instead, we built a tool that does it empirically. So we create a whole bunch of data sets, and we sample we sample from each of them. But now we make sure that the data sets, the big code sets, are actually code sets with bad agreement. We construct the null hypothesis. Then we take the kappa of each of these sets, which was from the null hypothesis, and we get a distribution of kappa under the null hypothesis. So now we can look at the kappa we got, we can see where it falls in that distribution, and if it's way out at the tail of the distribution, we can quantify the likelihood that we would be finding a kappa like that if the null hypothesis was correct, if we reject the null hypothesis, and so on. This is called the Monte Carlo rejective method. And basically everything that I just said, you could ignore other than the fact that you should use it. It's called RHO, it's our R package, RHOR, and there's also a website where literally you take your test set, you paste it in, it tells you your kappa and it tells you your rho. So very easy to do, and I'll come back to that in a bit. What it means, though, is that now when you provide a value for kappa, you can also statistically test whether it's significantly above whatever threshold you chose. We've gone a step further and built this into a code development tool called the encoder. I'm not really going to have time to talk about it, although there's stuff online, and I can connect you with some students who use it, and I'm happy to talk more about it one-on-one. But basically, it takes advantage of the row statistic to use active machine learning to generate codes. So it's optimized to generate codes that are valid, that are transparent, meaning you actually can see what's causing the machine to code the way that it did. Works on small excerpts of text, so a lot of unsupervised methods have trouble using small text snippets because they're looking for correlations. It works on small numbers of examples, so you don't have to have a huge corpus of data in order to be able to generate like an LSA space or something. And most important, it requires minimum human coding. It's actually been optimized to require the least work on your part as you generate the valid automated classifier. All of which is just to say, this extremely important step in qualitative research is something that we can also use statistics to get a quantitative warrant for. That is, we can say not only is this code valid because you have looked at a lot of the data and you have coded it carefully, but also that's in a statistical sense, it's reliable across two humans, or even better, it's reliable including a machine which can now code lots and lots of data. I think of this as like a sort of a statistical Geico detector, right? Garbage in, garbage out. My codes aren't good, everything that follows from them is going to be nonsense. So this is a really important step. But I didn't just, now notice though that I didn't just tell you about the codes, I also talked about how they were connected to one another. And I told you the story about, showed you how they were connected within one group of students, but you might reasonably ask, well, is that the only time that happened? Or is this something that was happening over and over and over again in your data, right? What a qualitative researcher would call theoretical saturation, right? If you've seen this thing enough times that when you look at more data, you're just going to see the same pattern. So in order to be able to construct some kind of model of this pattern, first we have to talk about what it means for these two things to be connected in this way. Well, we've actually seen this already, right? So when Michael was asking about data, he was asking about it in response to this discussion of technical requirements. So what we can do is take, for example, data and technical requirements, these two codes, and we can just pick a line of the data and see, are those two codes connected in it? Well, in this case, no. But we also need to look back a little bit in the conversation. There's a little window of time prior that we want to consider because, of course, these lines aren't just spoken in isolation. People are in a conversation. We still don't see anything, so we can slide this little window down. It's called a moving window, actually, or stanza window. We slide it down a little more. Now, notice, though, that we don't want to look back forever in the data. Why? Well, because it's true that if two people are having a conversation, each one has to remember what the last person said. Otherwise, it's like driving to Thanksgiving with my grandmother and my Aunt Florence, where the two of them were each having a conversation, taking turns, just neither conversation had anything to do with the other. Right? And in fact, ideally, you don't just want to remember one back, you want to remember a certain distance back in order for the conversation to be a good one. But notice the size of that window, the size of that stack, if you will, doesn't actually depend on how far, if I'm talking with you, it doesn't depend on how far back I think how far you can remember. It depends on how far back I think you can remember. Because if I think that the thing I'm about to talk about is past the part of the conversation that you've gotten kind of in your active memory, I will reach back and reintroduce it in order for it to be part of the conversation. So as a result, those windows aren't infinitely long, and they tend to have a certain stability to them, more or less because we don't trust each other. Right? We don't want to assume that everybody is too smart. So this window is called the common ground. Sometimes it's called recent temporal context. There's a small difference between them. But the basic idea is it's the things that when Lena says this, she assumes everybody else was thinking about, and in particular, she's thinking about. So we take this window and we slide it along, and then when we find a connection, we can mark that as a link between the two ideas. Go to another line, and maybe different ideas will be linked. Go to a third, and maybe they're linked multiple ideas. And if we add up all the different links across all the different lines, we get a model of the way in which ideas have been connected across either an individual or a group of people or whatever, however we read our model. This is, by the way, called epistemic network analysis. And what I'd like to do is just show you a brief film clip to give you a kind of more visceral sense of how this works. So the clip is from Law and Order. And I'm going to show it to you twice. So the first time, what you'll see is the actors and the transcription of the dialogue. So you can think about that as like what your data would look like if you were analyzing this film clip in many cases. And then the second time it'll be the same clip, but now you'll see the actual network models being formed as the speakers are talking. It's like a 1.5 minute clip.
Flat, almost dissociative.
You think she's setting the stage for a psych defense?
Well, it'll be hard going if she is.
Because she's faking it.
No, because DSM-4 diagnostic standards still don't exist for postpartum psychiatric illnesses.
Here we go.
Many courts bar its admission. That's the reason why infanticide sentences vary so wildly in this country. Some women are given the death penalty, and others are given probation.
You think postpartum depression should excuse murdering your child?
It's not depression. I think she's suffering from postpartum psychosis.
Giving birth made her crazy.
It's a hormonal imbalance stemming from pregnancy. Its onset can be quick and severe. Its symptoms include agitation, hallucinations, delusions.
The Andrea Yates defense.
Look, the only thing making this girl crazy is the baby's father. I don't know what part he played, but I know that he's involved.
Her affect was flat, almost dissociative.
You think she's setting the stage for a psych defense?
Well, it'll be hard going if she is.
Because she's faking it.
No, because DSM-4 diagnostic standards still don't exist for postpartum psychiatric illnesses.
Here we go.
Many courts bar its admission. That's the reason why infanticide sentences vary so wildly in this country. Some women are given the death penalty, and others are given probation.
You think postpartum depression should excuse murdering your child?
It's not depression. I think she's suffering from postpartum psychosis.
Giving birth made her crazy.
It's a hormonal imbalance stemming from pregnancy. Its onset can be quick and severe. Its symptoms include agitation, hallucinations, delusions.
The Andrea Yates defense.
Look, the only thing making this girl crazy is a baby's father. I don't know what part he played, but I know that he's involved.
Liv,
So when we first watch the clip, we have a sense that these three people have a different perspective on what's happening in this case. And now we can see a mathematical model that represents some of those differences. So for example, George is very focused on the postpartum psychosis diagnosis, which is represented by the thick connection between those lines. Donald is focused more on infanticide and the judicial system. And Olivia is focused more on deception and the father. And it turns out actually Olivia's right. Watch the Law and Order. But in any case, the idea is that we now have a way of representing the differences in how people are speaking in a way that's quantifiable, but also makes sense in terms of qualitative or ethnographic approach to data. So, for example, I showed you data from this team. Well, here's what their epistemic network, the group's epistemic network looked like. Here's Michael's network across the work of that team. And if you remember, Michael was the one who talked about data in response to technical requirements. Well, that's right here. Right. Similarly, if you remember, Elizabeth was talking a lot, was the one who made the link between design trade-offs and data, right here in the data. Now, some of you may be thinking, well, where did that network come from? I just said, okay, we make connections, and I put these dots up, and now I'm saying, oh, we have this network. Well, so I'm going to take a second, and I'm going to explain some of the mathematics underneath this, but if you're math phobic or aren't interested, you literally just tune out, check your email for the next 45 seconds or so. If you don't miss anything that's critical, I'll let you know when we need you back. Okay, so basically any network is just a matrix. You can treat a matrix like a string of numbers, like a vector in a high-dimensional space. So we project the matrices into a high-dimensional space. We do a dimensional reduction, and then the points that are in the space are the place where each matrix appears under that particular projection. And then we place the nodes that represent the codes in our model in order to, we use an optimization routine to place those. Okay, so everybody else, if you don't do your email, come on back. What you want to know is that we place those nodes such that if a network has a point over here, its connections are strongest on that side of the network graph. If its point is over here, then it has connections that are stronger on the other side of the graph. And what that means is that there's a relationship between those networks and the underlying points. So for example, Michael's network is up here because he made connections between technical requirements and data and design and technical requirements and design trade-offs, or most connections, which is up at the top part of the space. Elizabeth was here because, as we saw, she had a strong connection between design trade-offs and data, which is lower down in the space. And if we look at Zachary's point, we could predict that his connection should be lower down still, and sure enough, that's what's happening. The reason that this matters is that now, instead of just showing you the data for one small group of students and inspecting each of their networks to understand what's happening, now we can compare larger numbers of networks. So for example, we could look at a group of advanced students, meaning students who had more experience in engineering who were using this simulation. We can look at what their mean, where their mean is in this epistemic network space. We can look at what their mean network is in order to make sense of why their mean is where it is in the space. Similarly, we can do the same thing for a set of novices. Now we can actually compare the experts and novices statistically by looking at their location in the space. So in this case, the experts and novices are statistically significantly different. And we have an R squared of 12%, which is a lot higher than 0.000025. We can also subtract the mean networks, one from the other, so we can see where the biggest differences between the groups are. And not surprisingly, the advanced students focus a lot on data, because that's a critical part of an engineering process, and the novices talk more about collaboration. Again, not surprising. If I took 4 of you and said, okay, work on this engineering problem, one of the first things you'd have to talk about is like, who's going to do what? Because you don't have any history of collaborating in this domain. We should also point out, by the way, that that basic layout is essentially the story that I just told you, which suggests that this story was not just a property of this one group, but at least for the advanced students was something that was happening over and over. In other words, what we're able to do is not only provide a warrant that goes from data to interpretation in terms of the codes, but also in terms of the patterns by which the codes are related to one another. Before I move past this, though, I'd like to make an important point, which is this represents an incredible compression of the data. For each of these data points represents thousands of lines of turns of talk for an individual across many, many individuals. We've kind of crunched this all down into just a single point. But we've done it in such a way that if we interrogate that point, we can actually see the network that it corresponds to. And so we can make sure that point's location makes sense in terms of the underlying network. And we can look at any one of the connections in the network, and we can see the actual data where that connection got made. In other words, the model has a certain transparency to it and allows us to do something that's critically important, which is to close the interpretive loop. Right? So we start with the data, we come up with an understanding of what we think is happening, we construct a model of that understanding, we apply that model to the data to see whether it appears to persist in general, but then we're able to come all the way back down and go and look at some other piece of data about which this model is now making an assertion, and open it up and see all the way down to the original data whether or not that assertion holds, whether the model makes sense. It's called completing the interpretive loop. And the point here is that there are 3 different ways in which we can make this connection between the world of data and the world of interpretation that go beyond just what happens in the qualitative processes, that is, they're using statistics, but also where those statistics are grounded. In other words, what we have is a set of grounded models. They actually come out of an understanding of the data, and they're not just patterns that a machine happened to find. They're based on meaningful variables that we're able to validate that those are meaningful. And they're not black boxes. They're subject to inspection, so we can see why they work the way they do. I've talked about engineering. Many of you probably don't care that much about engineering, so let me just talk for a second about Shakespeare before I close. So we also have looked at the works of Shakespeare and did some automated coding on them. My daughter actually coded the work of Shakespeare for 10 different codes using our encoder tool and got valid agreement in about 4 hours, so that's pretty good since she's a first-year student in college. I mean, I wouldn't compare her to a Shakespeare expert in terms of the quality of the codes, but at least she was able to do it. So, right, Hamlet, as you know, is a play where a young man is conflicted because his uncle has killed his father, and then his mother has married his uncle, and he's not sure whether he should kill himself or kill him or kill her, or really who to kill, essentially. In Romeo and Juliet is the story of 2 teenagers who fall in love, and they make the mistake of falling in love with somebody who is from a family who's in a feud with their family. And so, not to spoil it, there's also a lot of death involved. So we made an ENA model, and now you're actually looking at the web tool interface for ENA. So this is obviously sort of a very simple model. It just has men, women, and honor in it. But even already we can see that there's a difference between the 2 plays. So to read this, Hamlet is represented in red, Romeo and Juliet in blue. The models on the right are the actual individual models for each play. And the model in the middle is subtraction between the 2 of them. The points are all different characters in the play. We can see that their means are, well, they're different, obviously, but they're not statistically significantly different. We can actually just measure that right in the tool. This is a Mann-Whitney test, because who knows whether those points are normally distributed. If we add love, which obviously is an important part of, and particularly of Romeo and Juliet, we can see we get some more distinction in the model. But it becomes really clear the differences between the plays when we add the central theme of death. So both of these plays are fundamentally about death, but they're actually about different kinds of death, represented in the fact that that concept of death is actually connected to different themes. We can go beyond that, and we can actually look at individual characters and how they relate to this pattern. So, for example, this is comparing Romeo in green with Hamlet in mauve. I don't really know what color that is. And we can see, not surprisingly, Hamlet talks a lot more about love and death, and Romeo talks a lot more about love and death, and Hamlet talks more about man and honor. Again, not surprising, but we know about the plays. We can compare Romeo and Juliet. Romeo is again in green. And interestingly, it turns out that Juliet talks a lot more about honor than Romeo does, connected to everything, which kind of made me think that, well, maybe Romeo's a little more selfish than I thought when I first read the play. And actually, if you go back and think about it, there's some truth to that. So I've showed a bunch of examples here, a couple of examples here, but this has been used in a bunch of different domains: engineering, urban planning, journalism, surgery, gaze alignment, internet search, drama, as I just showed you, and more. This slide's actually out of date. And I focused on ENA as one particular tool, but we could also have used HLM or topic modeling or sequential analysis or Bayesian networks or lots of other tools to capture quantitatively the pattern that we were seeing in the qualitative data. What matters is that what we're talking about is grounded models with meaningful variables that are not black boxes. If we don't do this, there's no way to take the oceans of data in which we swim and turn them into meaningful models that will tell us something about the kind of thinking that students need to do. This is the basic project of quantitative ethnography, to try and provide both the conceptual and the pragmatic tools that we need in order to be able to bring these worlds together. Before I completely stop, I just want to thank our sponsor, NSF, which has given quite a lot of money to this work over the years and really made it possible. I should also point out that when I say we, I'm referring to lots and lots of people, not just to me and my own students in lab. We have collaborators around the world, all of whom have contributed different pieces to the puzzle of understanding how to do this. I have a great lab of students and staff at UW, and one of the great things is that part of our funding pays them to help you. So if you're interested in learning to use any of these tools, let me know, or just contact us through our website, and we can actually set you up with somebody in the lab who can help you make a first model or models with your data so you can sort of see how things work. I've talked about 3 different tools. They are all available in an R package if you're a sort of power user and have really, really big data. And they're also available in web versions. The links for all of that are at epistemic.org. And look, so you should do this. You should use Rho. Why? Because you're actually doing bad science if you ignore the fact that there are type 1 errors and that we can control for them. It's one thing if nobody knows how to fix the problem. It's still bad, but at least you're doing what everybody else is doing. Now that we know how to do it, there's no excuse not to. And here's the thing. When I say this to graduate students, the first thing they do, and professors too, but less so, is they groan. And they say, you mean now in addition to getting iterator reliability, I also have to test it, and you're going to tell me that my IRR is no good? But that's not the right way to look at it. The job of statistics, remember, is to tell you how little data you need in order to make a claim. And what it turns out is that if you actually do this in a sound way, you can estimate the size of a test set that you need, and it's usually much smaller than you think. So I really encourage you to do that. These other tools, use them, don't use them. They have some really useful properties, some of which I've touched on here. But whatever tools you choose to use, the trick is that you're going to somehow have to integrate quantitative methods to make sure that your findings are statistically significant, and qualitative methods to make sure that they actually mean something. I've talked about this in more detail in the book, Quantitative Ethnography, but as I say, there's also a website and human resources that you can go to as well. So I know it's late in the day. Let me stop there and thank you for coming late in the day. And I'm happy to take maybe a couple of questions for the whole group, and then maybe we'll stop, and if people have individual questions, they can come up so people don't have to stay too long. Yeah.
Thank you so much. That was really new to me because I have done some qualitative analysis, not linking qualitative and quantitative together. But one question came to my mind. First of all, we needed software to do this kind of, to draw this kind of patterns out of the data. Yeah.
Well, it depends on what you mean by draw. So to actually find patterns in the
You
data.
have the data and you want to find a kind of pattern within the data. So we cannot do it by hand. There should be a software to, draw the lines, link the words together.
So you mean to actually construct those models?
Yeah.
So technically you can do it by hand. The only parts that would be difficult to do without a computer are the dimensional reduction and the placement of the nodes. You could do it by hand otherwise. I don't recommend it because it's a lot of work and the machine does it much more quickly and accurately. But yeah, somehow and which will raise an interesting point. This may not be exactly what you're asking, but it requires you to take your qualitative data and give it a well-formed structure in a data table. The book talks, actually there's a whole chapter basically about that, about how you get your data into a form that is valid from a qualitative point of view, but also will work in terms of statistics. But yes, essentially if you want to do this, at some point you're going to have to use the computer to run some of these analyses.
Yeah. Specifically on the data, a corpus, for instance, in language, in linguistics, you have corpus analysis.
Yeah.
So I have a lot of data.
Yep.
And then the next question is, how is this different from frequency analysis? Because we can do the same with frequency to say that in this, let's say, novel, the number of the words love, for example, has a repetition of 2,000 or 3,000.
Yep. No, this is a great question. Yeah, this is a great question. So people know that frequency analysis is basically you're literally looking at word frequencies, and it's not. You do some stemming. So love, loves, love. Those would all count as the same word typically. So the biggest difference is that this is based on codes, and in particular on big C codes, meaning things that you, as the analyst, think are meaningful in the culture that you're trying to analyze. The word love and loves and loved and other words that mean the same thing as love all actually have a semantic relationship, and what you're doing with the small c code is you're capturing all of those and you're saying that there are categories of experience that are important.
So that is why I asked for the software, because there should be a software to make a distinction about the relationship among the words. Semantic analysis is something which is very difficult to see how these two words are related.
Right.
Because there are some words which are closely related, but there are some others which are weak relation. There's a feature, the number of features of this word is 10, the number of features of the other one is 9. Out of these 9 and 10, just 5 in common.
Right.
Between two other words, we have 4 in common. And this is something which is complicated.
Yeah.
There should be a software to do this.
Well, so I think what you're suggesting is that there are ways to come up with the appropriate small c codes, that is to develop a classifier for a concept that leverage the fact that we can use statistical analyses of the word frequencies and their co-occurrence and so on. That is one approach to doing it. The challenge often is that if you take how long it takes to run the machine model, plus how long it takes to actually get those codes validated by comparing them to multiple humans. Right? If you add those things together, it's often more efficient to use the approach that we take, which is this kind of active machine learning. But of course, the point of quantitative ethnography is not that there are some specific tools you should use, although you should use Rho. Right? But other than that, the point is not that there's some specific set of tools you can use. But it's a way of thinking about how you use those tools. And as you point out, there's sort of a number of steps in the process. And whatever tool is going to be best for your data at that step is fine to you. Yeah.
I have a question specifically about the discourse.
Mm-hmm.
So do you have to have everything in text for this to work? Are you inputting categorized text into the program?
Yeah. So what sort of data? Give me the counter example that is obviously in the back of your mind.
No, I was just. Have you heard of Kimberly Tanner?
Mm-hmm.
So she does discourse analysis in large lecture courses to see how much partner work is going on versus lecture talking.
Mm-hmm.
So I was just wondering if, I guess because her system uses just decibel analysis, if there would be any way to differentiate what's going on in a classroom more.
Yeah, so again, this is now the parallel of the previous question, right? This system depends on having categories of meaning, right? So if you assign categories of meaning to the decibel levels in some way, then all from like an E&A perspective or from a quantitative ethnographic perspective we care about is those categories. They don't have to be binary. You can use continuous numbers too. But the point is that there has to actually be some category of experience that you're capturing, whatever the data source is. So that means this can work. You can do this with video analysis. You can do it with multimodal analysis. You can use multiple different data sources. Because the key link is I have a bunch of different sources of data. There are different small C codes for each of those sources of data, but they're all pointing at the same big C code, if that makes sense. That having been said, most of these tools work very well if your data can be represented in text. So for example, if you're doing gesture analysis and you have some encoding system for the gestures, right, then systems like the encoder and so on can process those as well as anything else. They're just using regular expressions, so you just tell it what constitutes the pattern you want to see.
Thanks.
Yeah. Any other questions? All right, well, let's stop there. As I say, I'm happy to chat with folks one-on-one for a bit. I'm in no rush to get anywhere. And feel free to drop me an email, or just you can find us through the website. And if you're interested in finding out more, there are people who will be happy to chat with you in the context of your specific data, concerns, issues, what you're wondering about. So thanks again. Bye, G.